Thank you so much for having me here today. I'm so excited to be able to share my research with you. So what I did is I taught the computer how to diagnose breast cancer so it could determine whether breast masses are malignant or benign. And now this is really important because 1 in 8 women are inflicted with breast cancer. And these statistics are just startling, and unfortunately, they're on the rise. It is really imperative that these women can have the best procedures available to them. The fine needle aspirate is currently the least invasive form of test a woman can have. It's also the cheapest, and it can lead to results that can be delivered as quickly as same day, so it can lead to earlier detection, which can create better treatments. However, it's so inconclusive that a lot of doctors refuse to use them, especially in the United States. They're used a little bit more frequently in Europe. So I created a computer program because I really want to revive the fine needle aspirate. I did this by creating an artificial neural network which models the brain's neurons and interconnections so it can actually detect patterns that humans can't detect. The current neural network is working really well. It is 99.1% sensitive to malignancy. And I've run over 7.6 million trials to prove that as I get more data, these success rates should increase while the inconclusive rates should decrease. And that's why I've deployed it to the cloud, so I can collect data from hospitals all over the world and so that it can be utilized all over the world. So what exactly is a FNA? The way it works is a doctor sticks a fine needle into a palpable breast mass and extracts a few cells. These cells are then stained and looked at under a microscope. Now this entire process is only going to cause the patient about the level of discomfort of a blood test. So the way fine needle aspirates would traditionally work is doctors would look at these cells and try to determine whether they were malignant or benign. The problem is the cytologies of these cells can exhibit both malignant and benign characteristics. So if you look at that top mass over there, you can see that the cells are about the same size and about the same shape. Now that's a really good sign. That means that the mass is probably benign. But if you look at those tiny dots in the cells, those are the nucleoli. There are multiple nucleoli per cell, and they're really prominent. That's not normal, and that's actually an indicator of cancer, even though this mass is in fact not cancerous. The middle mass is cancer, and the cells on first glance, they're kind of irregular. They're different sizes, kind of all sprawled out. Except for the really light cells, they're actually devoid of cytoplasm, and that's a characteristic of a benign mass. And then the bottommost mass, again, is not cancer. That's great. And you can tell that because the cells are really close together and compact, great marginal adhesion. However, the darker areas are actually would lead a doctor to think that could be cancer, because that means that it's multi-layered in those areas, and that's an indicator of cancer. The thing I'm really trying to show here is that these diagnostics aren't cut and dry, and this is why physicians struggle with them and why they're moving away from the fine needle aspirate. So I wanted to create a computer program that could analyze these patterns. The way I did that was by creating an artificial neural network, and what it does is it feeds in attributes as inputs. Things like clump thickness. Are the cells mono or multi-layered? Because being monolayered is an indicator that you might not be looking at cancer, whereas being multi-layered is often an indicator that you're looking at a tumor. There are things like bland chromatin, and that's going to rate the uniform texture of the chromatin in the nucleus. Because if it's fine, that's a great sign the mass is probably benign. But if it's really coarse, then that means it's probably going to be moved soon. That's an indicator of cancer. So these numbers are going to come in on a scale of 1 to 10. 1 being this is a very benign-looking attribute, 10 being this is a very malignant-looking attribute. Of course, this is the real world, so we're not going to hit the textbook cases very often. Often they'll fall within the 2 to 9 range. So these become the logical inputs to the neural network. The neural network is then going to convert these inputs into 4 nodes of their binary representation. The reason why it does this is because the digital spike is actually a lot like the binary spike. Because binary numbers are 1s and 0s, the neurons in the brain are firing or not. And the whole purpose of this computer program is to be brain-like, so that helps a lot. In addition, the artificial input layer is then going to make 216 connections with the hidden layer. What's really cool is the way neural networks model the brain's interactions is actually via math. So all of this is math. Inside, the artificial input layer is going to be multiplied by a corresponding weight matrix. And the computer is actually going to figure out the optimal numbers to put in that weight matrix. These weighted inputs are then going to be summed up via a summation function that are each going to each node, and then sent to a sigmoid activation function. The sigmoid activation function is going to convert the number on a scale of 0 to 1. 0 being this node is off and not firing, 1 being this node is going strong, and of course, you've got all the numbers in between. That then becomes the output of the hidden layer, and a similar process is going to occur between the hidden layer and the output layer, so that the computer can ultimately reach a diagnosis. Now, this is a backpropagation neural network, so it's constantly going to be updating itself. It's constantly going to be learning based on its mistakes. If you think of what that means for cancer, cancer is constantly mutating and changing. So my neural network will be able to change itself and adapt as cancer adapts over time. So I threw out some words like some different functions. I just want to show you what they are. These are the components of the program. They're the sigmoid function, the summation function, the step function, and the inconclusive assessment. Now the sigmoid function is actually the activation function. So like I said, that's going to determine how much things are firing. And then those lines that you saw that replicate the synapses in the brain, this is actually what's going on in between them. So for example, in the from the artificial input layer to the hidden layer, you have the summation and the sigmoid function. From the hidden layer to the output layer, you're going to have a few more functions, the step function and the ultimate diagnosis, because that's where you have to reach whether that particular neural network thinks it's malignant or benign. Now, programming a neural network is not an easy task. It's really difficult to get the computer program to all work together and come together. So I'm not scared to admit I actually failed twice at this before I was successful. The first time, there were more errors than code, so the entire network was scrapped. The second time it compiled, I was really excited, and I started running my tests, and it was solidly worse than flipping a coin at diagnosing breast cancer. I think the success rate was like 45%. So that was also scrapped. But the great thing about science is you learn just as much from these flopped experiments as you do from your successful ones. So I was really able to take the shortcomings of the first two experiments and apply that to create a third implementation that works really well and could be hospital ready. Some of the reasons it's working so well is one, it's training and using original base data. There's no doctor going in and discarding any of the outliers, and there's no doctor saying, pay more attention to this attribute. I'm letting the computer use its brain entirely. And it's worth noting, I got my original base data from the University of Wisconsin. They published a study as public domain on the UCI Machine Learning Repository. So I was able to get 681 samples to train the neural network with. In addition, I have this artificial input layer. And not only does that make the program more brain-like, but it's also going to limit the numbers so they don't get completely massive while other numbers become minutely unimportant, since they do start at such low values. I also have heavy malignant weighting because it is imperative to diagnose cancer patients correctly because those are the diagnostics that are going to save lives. So on a scale of 0 to 1, I'm only going to call the mass benign if it's under 0.2 because I want to make sure those cancer patients do receive the best diagnosis possible. And then my inconclusive logic is really kind of cool. So in computer science, it's often considered failure not to have an answer. But in medicine, it's really important to know what you don't know. So I researched different ways to try to come up with the best inconclusive logic. And I found that most programs were doing it based on those inner values of that sigmoid function over there. Now the problem is you saw the FNAs. They're really difficult to diagnose. And if I were to do my inconclusive logic that way, my inconclusive rate would be through the roof because a lot of the samples are actually going to be in that inner value. So instead, I simultaneously create 10 different neural networks. And since they're all randomly initialized a little bit differently, they all learn a little bit differently, just like we would all learn a little bit differently. So for the truly inconclusive samples, they're going to have different responses. And so they vote. And if they don't all agree on whether a mass is malignant or benign, then that's how a sample is deemed inconclusive. So after I had my neural network working really well, I put it into the Google App Engine because the Google App Engine gives me the scalability to support usage by every hospital in the world. Right now, I'm using it, a few hospitals are using it, but 1 million hospitals could use it tomorrow, and I could expand to other servers. In addition, building it as a web application, in the cloud allowed me to build it as this web service. So right now, I've built it as a web application. You can go on to cloudforcancer.appspot.com, and it's working great. However, I actually built my program where it's just this entity in cyberspace that's looking for a message to call it. And bear in mind, the whole purpose of my program is to create a tool for doctors to use. And in order for a tool to be viable, it needs to be convenient. So the great thing about the web service is I can code platforms to put into old PC systems for hospitals that are still using those, or into mobile tablets as doctors move forward using those. My physician uses a mobile tablet right now, and so I think that a lot of doctors might move towards those. And as future technologies emerge, I'll be able to have the capacity to handle them. And that's what makes the cloud great for a project like mine. And so this is what you would find if you went on to cloudforcancer.appspot.com. Physicians would pick from drop-down menus and rate all of the attributes on a scale of 1 to 10, and then they would click send. And if the networks have already been initialized, then they're going to receive a response almost instantaneously in under a second. So the current neural network is working really well. It is 99.1% sensitive to malignancy. And this is a number I keep coming back to because this is a number that could mean the network is hospital ready and a number that could mean it can save lives. In addition, that's almost 5% better than the leading commercial product. And I don't mean that there's neural networks out there testing breast cancer right now, but rather I customize off-the-shelf products, and there's like these products that you can not code a neural network, but it'll let you create one. So I tested 3 of those, and the custom-coded network that I did in Java was a lot better than the best of those 3 networks. In addition, I still retain a 96.53% specificity, which means it's still diagnosing most of the patients who don't have cancer correctly. And going forward, I did run these 7.6 million trials because I've proven that as I get more data, I can get more success and have less inconclusivity. So I really think that's the future of the program, and that's why I'm trying to get more data and more institutes beta testing it. Because when I was able to use all of the training data and test against the network once it had trained with all of the training data, then the network was actually 100% successful with only 4 inconclusives. Now, of course, I have to simulate how it handles new patients, so the numbers you were seeing with the 99.1, that was leave one out testing. So I'm really excited about the future of this program, and what's really great is after winning the Google Science Fair, I've really had this global platform that I can use to share my research with the rest of the world. I mean, just at the Google Science Fair, I got to share my research with scientists who are the who's who of science. I mean, computer science project talking to Vince Cerf, it doesn't get much better than that. I also got to talk with Ada Yana, the chemistry Nobel laureate, and their insight was just incredible. I also got to present at Google Zeitgeist, and I've gotten to give these TED Talks where I can share my research with professionals in the field. I presented to breastcancer.org and Lincoln Medical Center, and I got to attend the UN General Assembly and watch them push through this program that's going to make more women interested in the STEM field. Yesterday, I was actually at CERN, and I get to participate in Trailblazer tomorrow and meet a bunch of other kids who share my passions. And coming to give the TED Talk and also just getting invited to schools, it's just been incredible to be able to share my research. And some really exciting things have come out of this publication and out of this platform. I've actually got my program working with 2 hospitals right now. It's working with Lincoln Medical Center in the U.S. because they're one of the leaders for FNAs in the U.S. And they're actually giving me more samples. So I'm almost up to 700 samples right now, and I'm really excited to be able to report this is helping my neural network get smarter. In addition, I'm working with an institute in Italy, and they're going to test my program's capacities against 400 dubious samples. So I'll be able to see how it fares against the most difficult samples to diagnose. In the future, I'm also working on applying it to other types of cancers. I actually recently acquired some ovarian cancer, and I think that my neural network is working really well now, where I can create a platform that can diagnose other medical problems and specifically other cancers. And then something I've learned from working with different hospitals is that there is a bit of a physician bias when you're having the physician rate the numbers on a scale of 1 to 10. And the neural network can learn to handle that and work around it, but what I'd really like to eventually implement is image analysis so that there's no bias whatsoever. So at this point, you've listened to me talk, and you might be wondering, why does this research matter? And in typical science fashion, because that's something I've learned from science, is that as you ask more questions, you get answers, but you also get more questions. So that's going to lead to another question. Who do you know that would benefit from better breast cancer diagnostics? Thank you so much for having me today.
I think that's phenomenal, Brittany, and I think you really proved that high school students really can change the world.
Thank
and you haven't even graduated yet.
Thank you.
So that's great. Has anybody got any questions for Brittany? And we'll use the mic so that it's on.
You mentioned your program is 5% better than a commercial program on sensitivity. How does it compare on specificity?
Right, so something that I've had to do in order to make sure that I get that 99.1% specificity is to, take away sensitivity, is to compromise my specificity a little bit. So it's about 1% less. It has a 1% lower specificity than the leading commercial brand, but it's really important to diagnose cancer patients correctly. And I also think that as I get more data, that number will go up because it will be able to distinguish those borderline cases a little bit better. And specifically, the Italy data should help with that a lot. So I'm looking forward to that number going up.
A terrific presentation. Thank you very much.
Thank you so much.
I read some rather terrifying studies that show there's a considerable number of false positives that actually go as far as surgery. So when you're talking about this 15%, or is it 15 out of 222? No, oh no, okay. So however many it is, this is just, you're putting somebody further along the chain for more conclusive tests from the doctor, I take it. I mean, there was a bizarre study a couple of years ago that had suggested that it would be better reducing the incidence of breast cancer screening on account of the number of needless surgeries that take place. So can you see this kind of avoiding that by just being a little more precise? And then a second question after that, if I could.
So the specificity is still really good. Less than 4% of the people who don't have cancer are misdiagnosed. The way that this would move forward is the women would have core biopsies, so you're not completely putting them under the knife, but you would have full tissues be extracted. Obviously, we want to avoid that, and I would hope that my program could avoid it. But it's really important that these women who do have breast masses have them biopsied, because even though 2/3 of the masses are going to come back as benign, not cancerous, the ones that do, if you catch them as stage 1 or stage 2, you have a much better chance of diagnosing them in the 90% remission rate. But if you get them all the way at stage 4, your odds of survival go down significantly. So I think it's still important to make sure we do catch these masses. Mm-hmm.
So the second question, this is phenomenal, just this new medical world of just massive data sets and statistical analysis, but that depends on being able to get the data. So can you see yourself as perhaps doing some advocacy for open sharing of medical records? I know, sadly, we used to have something called Google Health, and we sunsetted it last year, which I thought was a great shame. But I know there's a push in the medical community to get this, but just how do you have these common data interchange formats and stuff? I mean, it's crippled government spending medically, but what do you see the future for being able to upload your DNA or your doctor's records to your social network and sharing that with some of these neural networks out there?
Yeah, so I got my data as public domain, and I could anybody can go on the UCI machine learning repository and download it. And as somebody who didn't work with a lab, one-on-one, I think I better than anybody know how important it is to get this data, because my study is completely dependent on public domain data. So I think that it'd be really important that people would feel comfortable putting their information out there. But I think it's also important that you can do that in a confidential manner. Like the particular study I'm using just has ID numbers. I have no idea who these women were. And I think that if we can create a platform to do that, then that would be great. And, I'd love to move forward with future acquisition of data samples that way on my website. But yeah, I definitely would be a strong advocate for that.
If this is a public domain machine learning repository, there are probably many other researchers looking at this data, trying various machine learning techniques to do the same prediction as you did. Mm-hmm. So I'm wondering, how does your results compare to other scientists' results in the field on the same data set, for example?
Yeah. So the data set was published in the early 1990s. So a lot of the studies that were done on this data was done back then. The people who published this data set was the University of Wisconsin. So they tried to work with the original base data, and they didn't get enough success. They didn't publish their study. But they then stripped it of over 100 outliers. They got 97.3% success, which was really novel for that time. But my sensitivity is a lot higher than theirs, and that's just a result of me working with the backpropagation, the innovative success factors I showed, and the fact that we are 20 years, 30 years with better 20 years with better technology. But I haven't found a study that's done as well as mine has, and it's really exciting to me, and I'm really hoping that my network can continue to do better as it gets more results. But there definitely have been studies out there, and I think that Wisconsin got the highest success rate from what I've seen.
I have a quick question. You talk a lot about the success rate and the interest in hospitals around your work, but I wanted to know if there had been any resistance. You talked a little bit about individual doctor evaluation of this data and how you've handled that and the feedback that you've provided to them.
So the hardest thing, particularly in the United States, is fine needle aspirates are practically obsolete. Like a lot of doctors refuse to use them. In particularly England and Italy, there's still a lot of fine needle aspirates being done. And the problem is there's this statistic out there that patients who are diagnosed with a fine needle aspirate aren't going to get as good of treatment and have a lower success rate. And that's completely bizarre because the reason that happens is that the countries that are solely relying on fine needle aspirates now are third world countries, so they can't provide as good of treatment. But some physicians don't look at that, so they don't want to use the fine needle aspirate. So my hardest task at hand is really convincing them to give the fine needle aspirate another try because it can reduce the invasion and lead to earlier detection, and these are things that patients need. And also, I'm a 18-year-old, so convincing them to give me data is always a little interesting.
First of all, thank you. It's very inspiring. I think all of us here enjoy programming, and it's beautiful when you can combine it with something meaningful.
Thank
You
you.
did it in a great way. My question was about the approach. I like the cloud approach, of course, but I'm also thinking about lots of women out there which live in remote areas. Think of Africa or in Asia, where the next internet connection is like miles and miles, if not hundreds of miles far away. I was wondering, like, if you thought about, like, once your model's been trained well enough, if you could kind of compact it into a mobile app that can work offline, which then can be used by doctors to take into these villages and do like instant diagnosis.
Yeah, actually, so I built, I have like the asynchronous method implemented. I just don't have it like as a mobile app quite yet, but that's definitely where I'd like to move towards the future because some doctors are actually already using mobile, even like in America are using mobile tablets in their practices. So I think anything that can make it more accessible is good. And the success rate of this is dependent on getting the whole world involved. And it's how many people can help is dependent on getting the whole world involved. So anything I can do to make sure that I can do that.
But it would also then work offline, or not? Would it also be able to work offline without an internet connection?
Without internet.
But you still need to have a cytology lab to actually make the
Yeah.
the tinting and get the pictures that you will evaluate.
There's no portable.
I guess I could create like a software package like the neural networks have, like the commercial neural networks where you could plug in a CD. I don't have any like platform for that yet. But the big problem is the neural network's constantly going to be learning as it gets this global, as people are depositing more data. So, I mean, it would be a shame to have to use the offline version because you wouldn't get the newest version of the neural network. But that would definitely be better than nothing. So I'll have to consider that. Thank you.
It's also to us to expand the internet connectivity to Africa.
Saw something in Zeitgeist that you guys were doing a pretty good job. So.
Thanks.
So I just have a quick question. I think your project has been inspirational to us, and I'm sure there are a lot of teenagers and high school students who are just thinking, you know, if I could do something this amazing. If you were to mentor, say, someone who's also interested in pursuing an ambitious project like this, what lesson would you want to impart, or what sort of words of wisdom could you say to somebody who's thinking they want to tackle a project like this?
I think there's two things. One, it's really important to follow your passion. I mean, I didn't start out saying, oh, I'm going to create this breast cancer neural network. I came across AI when I was in a 7th grade, which would put me at around 13, course on futuristic thinking. And I was enthralled. I went home and I bought a coding book and decided to teach myself how to code. And my first neural networks played soccer because I love soccer. So I think that it's really important to just do what you love and not focus so much on the end product because we're young, we get to experiment. And if we're not enjoying science, we're not going to pursue it. I mean, this project took me over 700 hours. And the other thing following that is it's really important to realize in science, you know, your flopped experiments are really successful. I mean, even when they're not successful, they teach you a lot. So it's really important to have that perseverance. And I think having that perseverance comes from having that passion. So.
I'm just curious if you could dream 5, 10, 20 years from now and where your research would be, where would you imagine that to be?
Well, where I would love for it to be is actually in real hospitals, diagnosing real patients. I'd really like to have it doing image analysis so there's no doctor bias. And, you know, it's just like any other tool that doctors use saying, oh, you know, yeah, we're going to biopsy you, put it into Cloud for Cancer, and we'll have the response in a few hours. And because a program can return the response almost instantaneously. So really it could be 5 minutes. So I'd love for it to just be global. And I'd also really like for it to be something that's not only specific to breast cancer, but working on ovarian cancer, lung cancer, because really the only limitation to the program's capabilities, because of course it's going to take a little bit more coding and such, but is the data that I can get my hands on. So that would be the ultimate goal.
Thank you.
No more questions, but I just want to thank you again. And an
Thank you so
amazing
much for having
project
me.
for an amazing 18-year-old.